Not a few centuries, not a few millennia, but 252 million years, to a moment when life on Earth nearly ended. It's called the Permian Triassic Extinction Event. Scientists sometimes give it a nickname, the Great Dying, or even more dramatically, the mother of all extinctions, because this was not just a bad day for dinosaurs. No, this was the worst biological crisis in our planet's entire history, an event so sweeping it erased 90, maybe even 96% of species. Imagine life as a bustling library, and then nearly every single book burned in one cataclysmic fire. Close your eyes and picture the ancient world. A single giant supercontinent. Pangaea stretched almost from pole to pole, vast deserts, endless coastlines, and creatures both bizarre and beautiful, crawling, swimming, and soaring through ecosystems now lost to time. Some had armored plates, some had sails like dragon spines. Some looked like distant cousins of animals we know today, though stranger, wilder, and more precarious. And then, almost in the blink of a geological eye, what happened? What could possibly wipe out almost everything? Was it fire, ice, poison skies, or the Earth itself turning against life in one of its violent spasms? That's the mystery we'll explore together. But for now, hold on to the image of that ancient world. Pangaea, alive with creatures we can barely imagine. And then silence. A silence so deep it reshaped evolution forever. So, as you drift with me into this story, I'd love to know if you found yourself in that moment 252 million years ago, what creature would you want to see with your own eyes before the curtain fell? Share your thoughts in the comments. And if you're curious about more journeys like this, tap like, subscribe, and settle in. Because tonight, we're stepping into Earth's darkest hour. Before the silence, there was song. Before the collapse, there was abundance. In the waning years of the Permian period, some 252 million years ago, Earth was not the stage of emptiness it would soon become. It was instead a world brimming with energy, variety, and daring experiments of evolution. To imagine it is to step into a grand pageant of life, one so rich and vibrant that the phrase "full of life" hardly does it justice. At this time, the continents of the planet had come together in a single sweeping embrace, forming the supercontinent known as Pangaea. Imagine Earth clothed not in scattered continents but in one colossal landmass, stretching nearly pole to pole, its edges fringed by vast oceans and its heart carved with deserts, forests, rivers, and mountain ranges. The geography alone lent the planet a drama we can scarcely picture today. From the air, if one could have looked down as from a bird or perhaps from a drifting cloud, Pangaea would have appeared as an enormous brown and green shield set into the gleaming blue of the Panthalassic Ocean, the world sea that wrapped around nearly everything. Along its eastern side, another vast water body, the Tethys Ocean, cut into the supercontinent like a deep sapphire wedge, promising coastlines rich with diversity and teeming with life. This land of Pangaea was no uniform plain. Its sheer size created extremes. Deep within its interior stretched enormous deserts, hotter than anything on our modern map. The continental interior was so far from the stabilizing influence of oceans that rain seldom fell, leaving vast stretches of land baked under relentless suns. Winds carried sand across endless dunes, while hardy plants struggled to hold on in patches of stubborn green. And yet, elsewhere on this same landmass, the story was entirely different. Along coastlines, rivers, and in wetter equatorial zones, lush forests spread their canopies wide, woven with ferns, seed-bearing trees, and towering plants that filled the air with oxygen and the ground with shade. The climate, like a great orchestra, played in contrasting movements. In some regions, it thundered with monsoons, the seasonal rains pouring down to nourish green belts of vegetation. In others, it whispered dry and barren melodies across dusty plains. At the poles, cold climates preserved ecosystems, unlike those of the tropics, giving the Earth a full palette of environments from the icy white of the south to the blazing reds and golds of the equator. Pangaea was vast enough to hold contradictions, rainforests, deserts, coastlines, and tundra, all woven into a single geological quilt. And upon this stage, life performed in magnificent variety. It was the time when reptiles had come into their own, filling ecological roles across land and water with striking inventiveness. Some prowled the forests and plains, others scuttled across arid stretches, still others lounged along riversides or coastlines. The reptiles were not alone, of course, but they were increasingly dominant. The Earth at this moment was alive with experimentation, as though evolution had been handed 1,000 brushes and told to paint in every color it could imagine. Forests stretched across much of Pangaea, especially in the wetter regions. These forests were filled with plants that seemed both familiar and alien. Some produced seeds, a relatively new trick in evolutionary terms, allowing them to spread more effectively than the spore-bearing plants of earlier ages. Others were vast ferns, with fronds unfurling like green flags, carpeting valleys and riverbanks. Towering trees offered shade and shelter, while tangled undergrowth provided havens for smaller creatures. To walk through one of these Permian forests would have been to step into a dense green labyrinth, humid and alive with buzzing, rustling, and the heavy scent of resin and soil. The air itself may have felt different, not quite the same as the atmosphere we breathe today. The balance of gases shifted across geological ages, and during the late Permian, oxygen and carbon dioxide swayed in patterns unfamiliar to modern lungs. Yet the forests thrived, and with them, entire ecosystems rose. Insects whirred through the air, darting from tree to tree, carrying out pollination and serving as prey for creatures waiting among the branches or along the forest floor. Beetles, dragonfly-like flyers, and other early insects had already established themselves as critical players in the ancient symphony. To a time traveler, their presence would feel oddly comforting, their buzz and flicker echoing the same rhythms we still see in summer skies. If the forests represented the green pulse of Pangaea, the oceans were its vast blue heart. Covering most of the globe, the seas of the late Permian were rich, layered and alive with creatures that swam, drifted, hunted and hid. Coral-like reefs, though different in composition from modern corals, rose in warm waters, creating undersea citadels for countless species. The reefs themselves were alive with forms of life we would recognize only faintly: coiled shells, spiraled swimmers, armored fish, and sleek predators, all weaving through a complex web of interaction. These reefs formed dazzling underwater metropolises, every crack and ledge hosting small scavengers, every open water zone patrolled by larger hunters. The open oceans, too, teemed with activity. Schools of fish shimmered like living clouds, each one darting in unison as predators lunged from the depths. Mollusks with intricate shells drifted or propelled themselves along, their spirals catching the light in strange, alien beauty. Crustaceans clambered over seafloor sediments, scavenging for scraps. Everywhere there was motion, everywhere hunger and survival danced together in ancient balance. Coastlines added their own drama. Where rivers met seas, estuaries created rich habitats for species able to tolerate both fresh and salt waters. Along sandy beaches and rocky coasts, creatures crawled, nested, or hunted for stranded prey. Tidal rhythms shaped the daily lives of countless organisms, just as they still do today, pulling the sea back and forth like a breath, revealing and concealing entire communities twice each day. Back on land, the diversity was no less astonishing. Reptiles, diverse, adaptive, inventive, had spread into niches that once belonged to other creatures. Some grazed in herds, cropping low plants in open spaces. Others prowled as hunters, sharp-eyed and sharp-toothed. Many lived in between, omnivores and opportunists, capable of taking advantage of whatever environment allowed. There were creatures that dug burrows, finding refuge in the earth. There were those that basked in the sun, bodies adapted to conserve or release heat as the climate demanded. Some carried elaborate displays on their backs or heads, possible tools for communication, thermoregulation, or intimidation. Evolution was experimenting boldly, and the land was alive with results. And yet, reptiles were not the only players. Amphibians still held their places in rivers, lakes, and wetlands, thriving in aquatic habitats even as reptiles spread across drier lands. These amphibians, larger and stranger than most we know today, filled the waterways with croaks, splashes, and ambushes. They were reminders that the lineage of life was layered, with new arrivals rising without completely displacing the old. The sheer biodiversity of the late Permian was staggering. In forests, insects and reptiles intertwined with plants in endless exchanges of energy. In rivers and lakes, amphibians lurked among reeds, while fish darted below. In oceans, vast reefs supported ecosystems of startling complexity. The Earth seemed to be hosting a cosmic feast, a banquet in which every niche was occupied, every opportunity for life seized. To imagine this time is to imagine abundance as the rule, not the exception. It was as if life had reached a crescendo, a triumphant swelling of diversity after hundreds of millions of years of trial and error. The evolutionary experiments of the Permian were not random splashes of color, but coordinated themes, whole symphonies of ecological interactions. Plants grew, insects fed on them, reptiles ate the insects, predators ate the reptiles, and the cycle spiraled onward. The oceans told similar stories, where plankton nourished small grazers, which fed larger hunters, which in turn became meals for the top predators of their day. The balance of ecosystems is often delicate, but during the late Permian, balance seemed to hold across vast scales, from the equatorial forests to the polar tundra, from the shallow reefs to the open seas. Life was not only surviving but flourishing. Each climate zone, each biome, each ecosystem added another verse to the Song of Earth, a song of resilience, adaptation, and beauty. And to witness it would have been to step into something almost overwhelming in its intensity. The forest would have thundered with insect wings and echoed with the movements of reptiles among the leaves. The deserts would have shimmered with heat as hardy plants clung stubbornly to life and reptiles carved paths across the sand. The oceans would have boiled with color and motion, creatures of every size and shape, weaving a dance as old as the time. Even the skies, though not yet home to the great flyers of later ages, would have carried their share of buzzing insects and perhaps early hints of gliding forms. It was, in short, a party, a planetary celebration of diversity, of abundance, of the sheer exuberance of life. Earth in its Permian prime was saying, "Look what I can do." It was a time of experiment, of expansion, of triumph. The ecosystems of the late Permian were as varied and rich as anything before or since, a testament to the resilience and inventiveness of life. And yet woven into this pageant of abundance was an invisible fragility. But that is a story for another part. For now, let us linger in the vision of Earth at its most alive, a world of deserts and forests, mountains and rivers, oceans that teemed, skies that buzzed, and land that crawled, basked, hunted, and it was a moment in deep time when the earth, like a great host, opened its doors to every form of life and said, "Come feast at my table," and feast they did. The forests rustled with countless wings, the oceans sparkled with shells and scales, the deserts shimmered with the resilience of survival. Everywhere, life, abundant, exuberant, defiant. The earth at the close of the Permian was a living jewel, spinning in space, radiant with energy and possibility. A world not yet touched by the shadow of the catastrophe that was coming. A world that knew only the fullness of life. When scientists look back at the end of the Permian period, 252 million years ago, they see not one neat, simple cause, but rather a wild and destructive cocktail of disasters, all poured into the same glass. To describe it plainly, the Great Permian Extinction was not the work of a single villain. It was an ensemble cast of chaos, a tragic orchestra where every instrument played out of tune at maximum volume. It was the worst ecological hangover the planet has ever endured. If you want to imagine what happened, picture Earth mixing a drink with every toxic ingredient it could find: volcanic fire, poisonous gases, runaway greenhouse warming, suffocating oceans, collapsing food webs, and perhaps even a cosmic rock thrown in for good measure. The result was a mass extinction so severe that nearly every living species disappeared. This was not a polite tragedy. This was global catastrophe in stereo. The first and most famous ingredient in this lethal mix was fire, or more specifically, the volcanic inferno of the Siberian Traps. The name may sound like a Cold War spy agency, But the Siberian traps were in fact a colossal volcanic province, located in what is now Siberia. During the late Permian, massive eruptions blanketed the land with flood basalts, lava flows that spread not just for miles, but for entire regions. Imagine rivers of molten rock stretching as far as the eye could see, piling up layer upon layer until the total volume dwarfed anything humanity has ever witnessed. These eruptions were not short-lived events measured in weeks or years. They persisted for hundreds of thousands of years, with pulses of lava and gas spewing into the air again and again. If Earth were hosting a festival, the Siberian traps were the pyrotechnics team that never stopped lighting matches. What made these eruptions particularly destructive was not only the lava, impressive though it was, but the invisible emissions riding along with it. Volcanic activity injects vast amounts of gases into the atmosphere, and the Siberian traps belched carbon dioxide at levels that would make modern climate change look like a mild rehearsal. Carbon dioxide, as most people know, is a greenhouse gas, meaning it traps heat in the atmosphere. The sheer amount released during these eruptions was enough to crank up global temperatures dramatically. The Earth warmed, and not in a pleasant beach vacation way. We are talking about a planet transforming into a planetary sauna, where average temperatures soared, polar regions lost their chill, and equatorial zones became nearly uninhabitable. Ecosystems that had once thrived under relatively stable climates now faced scorching, prolonged heat waves that bent plants, stressed animals, and reshaped habitat. And it wasn't just carbon dioxide. Alongside carbon dioxide came other volcanic gases, particularly sulfur dioxide. This gas has a strange dual nature. In the short term, sulfur dioxide can cool the Earth by reflecting sunlight back into space, creating temporary volcanic winters. But as the atmospheric chemistry balanced out, the longer-term result was acid rain. Sulfur dioxide reacts with water vapor to form sulfuric acid droplets, which rain down across continents, burning leaves, acidifying soils, and poisoning freshwater systems. Imagine an endless drizzle of liquid, with the attitude of battery acid. Forests weakened, rivers soured, and creatures that relied on freshwater habitats struggled to survive. What one hand of volcanic gases took away through heating, the other lashed with corrosive rain. Meanwhile, in the oceans, the situation grew dire. Carbon dioxide dissolves readily in seawater, and with so much of it flooding the atmosphere, the oceans absorbed enormous amounts. The chemistry shifted, tipping into acidification. For marine organisms that depended on calcium carbonate shells and skeletons, this was disastrous. Acidified waters eat away at calcium carbonate like vinegar dissolving chalk. Reefs crumbled, shells thinned, and the intricate architecture of marine ecosystems collapsed. Creatures that had once flourished in reefs found their homes dissolving around them, while plankton populations wavered, undermining the very base of the food web. It is no exaggeration to say that the oceans, once vibrant theatres of life, became corrosive traps where survival itself turned into a near impossible gamble. But acidification was only part of the oceanic nightmare. As the climate warmed and circulation patterns shifted, the oceans began to lose their oxygen. This phenomenon, known as anoxia, meant vast stretches of water became effectively suffocating. Fish, mollusks, and other marine creatures that required oxygen found themselves gasping in seas that had turned stagnant. Entire regions of the oceans became dead zones, expanses of lifeless water where only certain hardy microbes could endure. And those microbes ironically made things even worse. Without oxygen, some microbes switched to sulfur-based metabolisms, belching out hydrogen sulfide, a gas both toxic and noxious. Hydrogen sulfide not only poisoned marine life further but also bubbled into the atmosphere, creating a kind of invisible planetary stink bomb. To breathe near coastlines under such conditions might have been fatal, as the gas is highly toxic to animals and humans alike. One can almost picture Earth rolling its eyes and saying, "Oh, you thought lava and acid rain were bad. Here, smell this." All of this together paints a grim picture. But we are not finished yet. For while the Siberian traps were doing their volcanic best to wreck the biosphere, other forces may have joined the act. Some researchers suggest that Earth also suffered an extraterrestrial insult at this time, a meteorite impact. The evidence for this remains debated, But hints such as shocked quartz grains and unusual isotopic signatures suggest that a cosmic visitor may indeed have slammed into Earth during the late Permian. If true, the result would have been apocalyptic in its own right. Dust and debris launched into the atmosphere, blocking sunlight, disrupting photosynthesis and plunging ecosystems into chaos. The idea of Earth enduring volcanic fire from within and meteorite fire from without is the very definition of overkill. It's as if catastrophe looked around and said, why not make it a combo meal? The interplay of these disasters is what truly makes the Permian extinction so devastating. Each factor alone would have stressed ecosystems, but together they created a cascade. Imagine being a forest plant during this time. You are drenched by acid rain, scorched by rising temperatures, and suffocated by shifts in atmospheric gases. Meanwhile, your soil is leaching nutrients, and the insects that once pollinated you are struggling in the heat. If you survive that, you still face the risk of wildfires fed by hotter, drier conditions. Now imagine you are a marine shell builder. The water you float in has turned acidic. Your shell is dissolving, oxygen is scarce, and hydrogen sulfide is creeping into your habitat. Your predators may already be gone, but so are your food sources. Life was besieged from every angle, a cosmic pincer movement of stressors all converging on the biosphere at once. One of the cruelest aspects of this catastrophe was its timing. Life at the end of the Permian was flourishing, diverse and well adapted to a wide range of climates. Evolution had painted the Earth in bold colors, filling niches with reptiles, insects, amphibians, plants, and marine communities of staggering richness. But that very diversity meant there was much to lose, and the interconnectedness of ecosystems ensured that when one strand snapped, the rest unraveled quickly. Plants stressed by acid rain weakened insect populations. Insect losses cascaded into reptile diets. Marine collapse reverberated onto land through disrupted climates. It was a global chain reaction. Consider also the sheer duration of stress. The Siberian traps alone may have erupted in pulses over hundreds of thousands of years. This was not a single punch, but repeated blows, each wave of eruptions renewing the assault with fresh carbon dioxide, more sulfur, more heat, more acid. Between these pulses, ecosystems may have tried to recover, only to be crushed again. The extinction was not only severe but relentless, leaving no time for adaptation. It was like running a marathon in which the finish line keeps being moved further away while the road itself is set on fire. To call this disaster multifactorial is accurate, but almost too gentle. It was not a tidy list of causes to check off. It was an unholy synergy, a set of forces that amplified each other in ways that made survival nearly impossible. The greenhouse warming worsened ocean anoxia. The ocean anoxia unleashed hydrogen sulfide. The hydrogen sulfide added to atmospheric stress. Acid rain weakened land plants, which fed back into carbon cycling. Add a possible meteorite impact, stirring dust into the skies, and you have a planet caught in a feedback loop of destruction. The Earth of the late Permian was not simply unlucky. It was overloaded, stretched past the breaking point by forces both internal and external. If one were to give the Permian extinction a tagline, it might be, "It wasn't just one thing." Modern audiences love simple explanations. A single asteroid for the dinosaurs, a single ice age for megafauna. But the end of the Permian laughs at simplicity. It was a kitchen sink of calamities, a convergence of bad luck, bad timing, and bad chemistry. It was the worst possible recipe, and the oven was left on far too long. And so the great dying unfolded not because of a single villain, but because of a conspiracy of disasters. Volcanic fire heated the world beyond endurance. Greenhouse gases smothered it further. Acid rain burned forests. Oceans turned sour and suffocating. Toxic gases seeped into air and sea. Perhaps even a meteorite delivered a final insult. Together, these forces turned a thriving biosphere into a graveyard. The lesson is chilling and strangely humbling. Earth does not need just one catastrophe to end life's party. It can mix several, let them interact, and allow the chain reactions to do the rest. The late Permian extinction was not a clean surgical strike. It was a messy bar fight in which every opponent joined at once. The survivors were not the strongest or the smartest, but simply the lucky few who endured conditions most creatures could not. The story of this extinction reminds us that life is both resilient and fragile. For hundreds of millions of years, Earth had hosted a symphony of ecosystems. But when the instruments of disaster joined forces, even that symphony was silenced. The mother of all extinctions was not the work of a single hand, but the combined force of many, a global pile-up that reshaped the planet, and though life eventually recovered, diversifying anew in the Triassic, the scars of that ancient cocktail of disasters remain etched in rock, fossil and memory. If Earth could have spoken at the end of the Permian, perhaps it would have sighed and said, "Too much, all at once." When we talk about global catastrophe, our imagination often runs to explosions, sudden crashes, and violent upheavals. But sometimes the most dangerous disasters do not begin with a bang. They begin with a simmer. The opening act of the Permian extinction was exactly this. Not a sudden apocalypse, but a slow, relentless boil, a geological soup left unattended on the cosmic stove. At first the world looked much as it always had, brimming with life and stability. Yet beneath its crust, deep in the mantle's restless heat, pressure was building. In Siberia, a vast and ancient landmass stirred, and when it began to release its power, the world would never be the same. The Siberian Traps, one of the largest volcanic provinces in Earth's history, did not simply erupt like the cone-shaped volcanoes we imagine when someone says eruption. No, this was not a dramatic Vesuvius blowing its top over a city. This was lava on an industrial scale, enormous cracks in the ground, split open, and molten rock spilled out in colossal sheets, covering the landscape for miles. Instead of a singular peak, these eruptions spread outward, drowning regions under rolling waves of basalt. The outpouring was so immense that if you stacked all the lava flows together, they would tower higher than the Himalayas. It was less a volcano and more an Earth-sized wound bleeding fire. At first, life went on. Plants still rooted themselves in forests. Reptiles still prowled the land. But slowly, silently, the atmosphere was changing. Each eruption did not only release lava, it released gases, gigantic amounts of them. Imagine the sky as a storage closet and Siberia as a factory with no concern for limits. Carbon dioxide came billowing out, molecule after molecule, carried into the atmosphere on hot plumes. Sulfur dioxide followed, sharp and acrid. Every eruption was like a factory chimney turned up to maximum, and the Earth had no ventilation system. Carbon dioxide is a familiar culprit in climate stories, but during the late Permian the sheer volume released was staggering. Layer upon layer of lava meant centuries, even millennia, of constant emissions. Each pulse was like adding another thick blanket over the planet. Sunlight still streamed in, but heat had nowhere to go. It was trapped, rebounding from the sky back down to the land again, raising average temperatures bit by bit. At first the change might have seemed subtle, barely noticeable over a generation. A few degrees warmer here, a slightly drier season there, but the process was cumulative. The Earth was drifting toward a new equilibrium, and that equilibrium was hotter, harsher, and far less forgiving. Sulfur dioxide brought its own mischief. This gas is tricky, a double agent of sorts. When first belched into the skies, it can reflect sunlight, cooling the surface briefly. Imagine the world covered with a thin veil, dimmed slightly like putting on tinted glasses. But the veil doesn't last. Eventually the sulfur combines with water vapor, forming sulfuric acid droplets. And when the clouds release that acid as rain, it does not refresh. It burns. Leaves sizzle, soils sour, and delicate ecosystems tremble under the onslaught. Forests that once spread their canopies wide began to falter, their growth slowed by relentless chemical assaults from above. The result was an atmosphere increasingly unstable. On one side, warming greenhouse gases turned up the global thermostat. On the other, pulses of sulfur dioxide caused short, sharp swings in temperature and laced the rains with acidity. This push and pull, this climatic whiplash, made conditions unpredictable. Seasons lost their balance. Some years burned, others chilled, all under skies that rained acid. It was as though the Earth could no longer decide what mood it wanted, swinging wildly from fever to shiver. For the creatures living at the time, this instability was insidious. Evolution had prepared them for the climates of the Permian, with its deserts, forests, and seasonal rhythms, but it had not prepared them for unpredictability itself. To survive in a desert is one thing, You adapt to dryness. You store water. You endure heat. To survive in a wet forest is another. You build your life around abundance. But to survive in a world where deserts might suddenly swing to floods, where fertile lands are washed by acid rains, and where the air itself grows steadily hotter with each generation, that is another challenge entirely. The greenhouse effect was especially cruel because it worked slowly but relentlessly. Think of it like sitting in a sauna where the temperature creeps upward, degree by degree. At first it feels tolerable, even comfortable. Then, after a while, sweat pours, lungs strain, and escape seems necessary. But there was no escape for life on Permian Earth. The supercontinent of Pangaea was vast, and although it contained deserts, forests, and polar regions, nowhere was immune to the thickening blanket of carbon dioxide. Even regions once buffered by oceans or rivers began to experience creeping heat. Over centuries, the entire climate system began to tilt toward extremes. The land bore witness to this change in subtle but unmistakable ways. Tree rings preserved in fossil wood show evidence of stress. Years of stunted growth, abrupt changes in rainfall, pollen grains tell the same story. Declining in abundance as forests faltered, dust layers in sediments reveal spreading deserts. The soil blown away as plants failed to anchor the ground. It was not a sudden collapse, but a slow unraveling. Earth itself was recording the instability, leaving behind a geological diary written in stone and ash. Meanwhile, volcanic activity did not let up. The Siberian traps continued to pulse like a sick heartbeat. Each new surge of lava meant another injection of carbon dioxide and sulfur dioxide. Every eruption renewed the cycle of short-term cooling and long-term warming. The skies grew hazy with ash. The air thickened with invisible gases. Day after day, century after century, the system tipped further from balance. Humor, strange as it sounds, has its place here. Imagine Earth whispering, "I'm just a little warm," while the atmosphere collects more and more carbon dioxide. As the decades pass, the whisper becomes a murmur, "I'm getting warmer," and eventually a shout, "I'm overheating." But by then, the planet was already locked into the greenhouse trap. The temperature rise was not a passing fever. It was a new reality. Animals felt the change in ways subtle and severe. Heat pushed creatures out of their comfortable ranges. Species that had once thrived in certain latitudes found themselves forced to move or perish. Some sought cooler refuges at higher elevations or toward the poles. Others endured as best they could, their metabolisms strained by rising temperatures. Those that could not adjust faced dwindling numbers, and always, in the background, the rain carried its acid sting, eroding forests, stripping nutrients from soils, and weakening the very foundation of terrestrial ecosystems. The early stages of this extinction event were, in many ways, invisible to the creatures living through it. A reptile grazing in a Permian forest would not have thought, the carbon dioxide concentration is rising. A tree unfurling its leaves in spring would not have known the atmosphere above it was changing. But the effect compounded nonetheless, seeping into every corner of life's web. Crops of spores declined. Predator-prey dynamics shifted. Insects buzzed through shorter lifespans. The changes were incremental, but like the slow tightening of a noose, the impact grew inevitable. The sheer persistence of volcanic activity made this instability unavoidable. This was not one eruption followed by recovery. This was eruption after eruption after eruption. The Siberian traps were not a one-night fireworks show, but an ongoing furnace, spewing for hundreds of thousands of years. Even during pauses, the damage already done lingered. Carbon dioxide remained in the atmosphere long after eruptions ceased, continuing to trap heat. Sulfuric acid clung to soils and waterways. The Earth could not heal between blows. This, perhaps, is what made the opening of the Permian extinction so uniquely sinister. It did not announce itself with a single catastrophic event. It crept in, like a shadow lengthening at dusk. It grew slowly until suddenly the world was darker, hotter, and far more dangerous. The instability was the warning shot, the tremor before the quake, the low rumble before the storm. And yet, for the plants and animals of the late Permian, there was no understanding, no force. There was only the experience of an environment becoming less predictable, less forgiving, less survivable. If one wanted to capture this moment with a metaphor, it would be a simmering cauldron. The Siberian traps were the flame beneath, steady and relentless. The carbon dioxide and sulfur dioxide were the ingredients, each adding flavor to the brew. The greenhouse effect was the lid, trapping heat inside, and the living world was the stew, bubbling slowly, uncomfortably, as the heat turned up degree by degree. The pot had not yet boiled over, but it was already too hot to ignore. And so the early onset of the Permian extinction unfolded not as a sudden catastrophe, but as a creeping instability. The world warmed, the skies turned sour, the rains grew harsh, the seasons lost their rhythm. Life found itself walking a narrowing path, hemmed in by forces it could not see, yet could feel in every breath, every leaf, every migration. The great catastrophe had not yet arrived in full, but its first act was already playing, and the curtain was rising on Earth's darkest drama. The oceans of the late Permian were once the crown jewels of Earth's ecosystems. They teemed with life, bursting with creatures that swam, crawled, drifted, or clung to coral-like reefs. For hundreds of millions of years, the seas had been a reliable sanctuary. Even when land suffered droughts, fires, or shifting climates, the oceans often carried on, stable and abundant. But in the slow march toward the great extinction, even the seas began to betray their inhabitants. What had been a cradle of life became a tomb, and the change came not with crashing waves or sudden storms, but with chemistry, invisible and insidious. The trouble began as carbon dioxide, spewed into the air by relentless volcanic outpourings, seeped into the waters. Oceans are not passive mirrors reflecting the sky above. They are vast chemical sponges. Carbon dioxide dissolves readily into water, slipping across the boundary between air and sea with deceptive ease. On a small scale, this process is harmless. It is in fact part of the natural balance that regulates Earth's climate. But when the atmosphere is flooded with carbon dioxide for millennia, the ocean's chemistry shifts dramatically. What had been a nurturing soup of minerals, salts, and gases became sour, corrosive, and hostile. To imagine this transformation, think of a glass of water into which you slowly blow bubbles with a straw. Each bubble adds a little carbon dioxide, lowering the water's pH, making it ever so slightly more acidic. Now replace that straw with the breath of thousands of volcanoes, and replace the glass with the entire global ocean. The result is acidification on a planetary scale. The seas of the Permian were turning into a cosmic version of vinegar. Diluted, yes, but corrosive enough to unravel the delicate structures upon which life depended. The victims of this transformation were, first and foremost, the creatures that built their bodies out of calcium carbonate. Shells, skeletons, reefs, all relied on the ability of seawater to remain saturated with carbonate ions. But acidified water stole these building blocks away. For ammonites and other shelled mollusks, their protective spirals began to dissolve. Imagine a snail whose shell slowly melts while it is still alive, its armor thinning until even the smallest predator or environmental stress could finish the job. Corals and reef builders fared no better. Their elaborate underwater cities, painstakingly constructed over generations, began to crumble as acid waters gnawed at their foundations. What had been bustling reef metropolises became skeletal ruins. The collapse of shells was not merely aesthetic. It was ecological dynamite. Shell builders form the backbone of oceanic food webs, serving as prey for countless fish, invertebrates, and larger predators. When their populations faltered, the collapse rippled upward. Fish that depended on them starved. Predators that depended on fish grew desperate. Entire food chains, once elegant and stable, began to buckle under the weight of absence. The collapse was not uniform. It was patchy, uneven, striking here, lingering there, but the trend was unmistakable. The oceans were losing their resilience. As if dissolving shells were not enough, another menace crept in, silent and suffocating. The loss of oxygen. Oceans are alive, not only because of their inhabitants, but because of circulation, the constant churning of currents that brings oxygen to deep waters and sweeps nutrients back to the surface. But warming climates disrupted these currents, slowing circulation and reducing the amount of oxygen delivered to the depths. The result was anoxia, Waters starved of oxygen, vast zones where gills and lungs found nothing to grasp. For fish, the situation was dire. Imagine swimming through your home waters, only to find them increasingly stale, the oxygen thinning like the air at high altitudes. Gills, no matter how efficient, cannot extract what isn't there. Schools of fish weakened, gasping in waters that had once sustained them. Some fled upward, crowding the shallows, desperate for oxygen-rich refuges. But even there, the concentration dwindled. The ocean itself was becoming a suffocation chamber. Ammonites, once masters of the seas with their elegant coiled shells, were particularly vulnerable. They needed oxygen not only for themselves, but also for their developing offspring, tiny creatures adrift in the planktonic haze. Without oxygen, reproduction faltered, entire generations failed, leaving gaps that predators could not fill. The spiral of ammonite shells, once symbols of resilience across millions of years, became gravestones in the fossil record, their intricate geometry silenced. The anoxic waters spread like ink spilled into a basin. At first they clung to the deeper zones, where circulation was weakest, but gradually they expanded upward, encroaching into mid-depths, then into shallower seas. Entire continental shelves, the regions most productive and diverse, became uninhabitable. Life retreated toward the surface, compressing ecosystems into ever thinner slices of habitable space. Predators crowded together, prey dwindled, and the oceans grew eerily quiet. The combination of acidification and anoxia was devastating, because it struck at different but complementary vulnerabilities. Acidification attacked the very structure of marine life, dissolving shells and reefs. Anoxia attacked the breath of the seas, suffocating fish and larger organisms. Together they created a nightmare scenario, a sea where you could not build and you could not breathe. For millions of years, the ocean had been a place of shelter, but now it whispered betrayal. The collapse of marine food webs was not instant, but it was inexorable. Phytoplankton, the tiny photosynthetic organisms at the base of the chain, struggled under shifting chemistry. Zooplankton that fed on them declined. Shell builders dissolved. Fish suffocated. Predators starved. Each step in the chain weakened the next, until the entire system began to teeter. It was like a game of ecological dominoes, except every piece was falling at once, and no hand reached in to stop the cascade. To call this event tragic is an understatement. The Permian oceans had been diverse and dynamic, home to creatures of dazzling form and function. Ammonites with their spirals, brachiopods with their hinged shells, corals with their reefs, fish with their sleek designs, all had thrived for millions of years. But against acid waters and oxygen-starved seas, their evolutionary brilliance counted for little. The chemistry of the earth itself had turned against them. If one were to add a touch of humor, bleak though it may be, it might go like this. The oceans were becoming a kind of cosmic soup, but not the hearty, nourishing kind, more like a pot of spoiled broth, too sour to drink, too stagnant to breathe. Creatures dipped into it found themselves not sustained, but poisoned. Earth, if it had a voice, might have muttered, "My seas are dying and there is nothing you can do but watch." The evidence of this collapse is written in the rocks. Layers of black shales, rich in organic material, tell of times when oxygen vanished and dead matter simply piled up, unconsumed, unrotted, preserved in suffocating waters. Fossil assemblages show the disappearance of once abundant groups, the sudden gaps where ammonites and brachiopods once flourished. Isotopic signatures record shifts in carbon cycles, testifying to the massive upheavals in ocean chemistry. The rocks do not scream, but they whisper the tragedy clearly. The seas turned hostile, and life could not endure. For creatures alive at the time, the unfolding collapse would have felt like betrayal. The ocean, once a giver of life, became an executioner. Reefs that had provided food and shelter melted away. Waters that had nourished became suffocating. Generations were cut short, food vanished, and predators wandered in vain, hunting in a sea that no longer sustained them. It was not a single moment of doom, but a prolonged tragedy, wave upon wave of loss, until the oceans themselves seemed hollow. The tragedy of the seas set the stage for the larger collapse of Earth's biosphere. For when the oceans faltered, the rest of the planet followed. Land ecosystems, depended on the balance of climates regulated by the seas. The carbon cycles disrupted by acidification and anoxia reverberated into the skies, feeding back into global instability. The collapse of oceanic productivity meant fewer nutrients cycled back onto land, starving soils and plants. What happened beneath the waves did not stay beneath the waves. It radiated outward, tightening the noose around the planet's living systems. And yet, there is something almost poetic, though grim, about the way the oceans fell, not with tsunamis or monstrous sea monsters, but with chemistry. Molecules dissolved, bonds shifted, balances tipped. It was the quiet cruelty of the invisible, the way a gas, slipping unnoticed into water, could undo millions of years of evolution. No creature could see the pH dropping, no fish could detect the creeping anoxia until it was too late. The tragedy was not theatrical, it was subtle, incremental, inevitable. By the time the seas had reached their nadir, the damage was beyond repair. Shell builders were nearly gone, fish populations collapsed. Ammonites, once icons of marine resilience, dwindled to a few desperate survivors. The oceans, once the planet's most reliable sanctuary, had become a graveyard. And yet, even in this graveyard, a few hardy species clung on, eking out survival in pockets where chemistry remained just tolerable enough. These survivors would inherit the post-Permian seas, evolving into the new rulers of the oceans in the Triassic. But in the moment the tragedy was complete, the seas had turned against life, and life could not win. The next act of the extinction would bring further horrors, but already the ocean's betrayal was clear. The seas, sour and suffocating, had undone their children. The ammonites spiraled into silence. The reefs crumbled, the fish gasped and failed, and the earth, if it could sigh, would have whispered, "My oceans are dying, and so is the world." If the early stages of the Permian extinction were a slow simmer, then what followed was the moment when the pot boiled over. The earth, already stressed by years of volcanic upheaval, now faced a new phase of disaster. It was not only heat or unstable climates anymore, but the very air itself turning treacherous. The Siberian traps, still in their volcanic fury, began to belch not just carbon dioxide but a cocktail of more sinister gases: sulfur dioxide, chlorine, fluorine and other halogens, chemicals capable of poisoning skies, corroding soils, and raining acid upon the land. It was the acceleration of catastrophe, a tipping point when the Earth's systems moved from discomfort into outright collapse. Sulfur dioxide, or sulfur dioxide, SO2, was one of the principal culprits. Every eruption pumped immense amounts of it into the skies, where it mingled with water vapor to form sulfuric acid droplets. These droplets drifted in clouds and eventually fell as rain. But this was no refreshing summer shower, no nourishing rainfall to feed thirsty forests. This was acid rain, sharp, corrosive, and unrelenting. Imagine a drizzle of diluted battery acid falling across the land, hissing as it struck leaves, soils, and streams. Forest canopies, once lush and vibrant, began to wither under the chemical assault. Leaves blackened, needles dropped, and bark cracked. The soil beneath, stripped of its nutrients by the constant wash of acid, grew thin and lifeless. Fertile ground became barren dust. The damage went deeper. Acid rain infiltrated rivers and lakes, lowering their pH and poisoning freshwater ecosystems. Amphibians, already sensitive creatures, were among the first to suffer. Their thin, permeable skins made them living sponges for environmental change, and under acid rainfall they faltered. Eggs dissolved in acidic pools before hatchlings could emerge. Streams lost their chorus of amphibian calls, replaced by silence. Freshwater fish fared no better, their gills burned by hostile chemistry, their young failing in acidic nurseries. The rain did not discriminate. It fell on every surface, corroding stone, leaching metals, and leaving behind a chemical signature still visible in rocks today. And sulfur dioxide was not working alone. Alongside it came halogens, chlorine and fluorine compounds released by the volcanic outpourings. These elements may seem harmless in the right context. Fluorine in toothpaste, chlorine in swimming pools, but released on a planetary scale, They became agents of ruin. Halogens have a talent for destroying ozone, the thin shield high in the atmosphere that protects the surface from ultraviolet radiation. As halogens spread, the ozone layer thinned, and the skies themselves became more dangerous. Sunlight, once a giver of energy, turned harsh and punishing. Ultraviolet rays scorched the land, damaging plant tissues and mutating DNA. Forests weakened further, their canopies thinning not only from acid rain, but from an invisible barrage of radiation. Breathing, that most basic of acts, became perilous. Sulfur dioxide in high concentrations is toxic to lungs, burning the delicate tissues of respiratory systems. For creatures of the late Permian, reptiles, amphibians, insects, and even plants exchanging gases through their stomata, air quality deteriorated into a hazard. Each breath carried not only oxygen but a sting of poison. Imagine living in a world where every inhale feels like smoke from a campfire, not once or twice, but every day, everywhere. For many animals, especially those without the ability to flee long distances, the simple act of breathing became a struggle. The forests, weakened by chemical assault and poisoned air, grew vulnerable to fire. Drier conditions, rising temperatures, and falling plant health set the stage. Then came the sparks, perhaps lightning, perhaps volcanic ejecta, perhaps spontaneous combustion of dry plant matter. Forest ignited, and once they burned fiercely. Trees already stressed by acid rain had little moisture or strength left to resist. Flames spread rapidly, consuming swaths of greenery, turning canopies into infernos. The smoke billowed upward, joining the volcanic haze, thickening the skies with soot. Ash fell like dark snow, layering over soils already leached of nutrients. The earth's surface became a theatre of fire, where each blaze left behind blackened skeletons of once thriving forests. These fires were not isolated disasters. They were part of the accelerating cycle of destruction. Acid rain killed plants, leaving behind dry, dead matter ready to ignite. Fires stripped the land of cover, leaving soils exposed to further chemical leaching. The combination created feedback loops, each disaster feeding the next. Smoke filled the atmosphere with even more particulates, further destabilizing climate patterns. The land was not simply stressed, it was unraveling. Life, already weakened by previous phases of the crisis, had little defense. Insects, once abundant and diverse, began to collapse in number. Their delicate wings and fragile exoskeletons offered no protection against acidic rains or toxic air. Pollination faltered, and plants lost crucial partners in reproduction. Reptiles, dominant on land, found their habitats shrinking into wastelands. Those that breathed deeply risked poisoning from sulfur-rich air. Those that sought shelter in forests found those forests burned to ash. Those that depended on plants or insects for food saw their supplies dwindle. Survival became less about thriving and more about clinging on, breath by breath, day by day. And yet in all this destruction there was a grim sense of acceleration, as though the planet itself had pressed down harder on the catastrophe pedal. Early stages of instability had been slow, almost patient, giving life time to adjust or migrate. But now the pace quickened. Acid rain did not wait centuries to alter forests. It struck in years, decades at most. Fires did not politely stop at rivers. They leapt across, consuming whatever lay ahead. The skies, once blue, became a murky haze, glowing dimly as sunlight scattered through a veil of gases and soot. Days darkened, nights glowed faintly with volcanic fires, and the rhythm of seasons blurred into a long disaster. Adding humor to such tragedy feels almost cruel, yet there is a dark comedy in the chemistry of it all. Imagine Earth as a careless bartender, mixing up a toxic cocktail, 1 part sulfur dioxide, 1 part chlorine, a dash of fluorine. Shake with volcanic fire, and serve with a garnish of ash. The drink is, of course, undrinkable, but the planet poured it anyway, and every living thing was forced to sip. Some gagged and perished immediately. Others lingered, weakened by each poisonous gulp, until they too succumbed. Earth, if it had spoken, might have shrugged and muttered, "Too strong? Well, I did warn you it was top-shelf poison." Geological records bear testimony to this acceleration. Layers of ash and soot preserved in sedimentary rocks, spikes in sulfur isotopes, evidence of acid weathering etched into ancient soils, all tell the same story. This was not speculation but fact written in stone. The land was scorched, the skies were poisoned, and the rain fell acidic. Fossil forests show sudden die-offs, with growth rings stunted or absent. Charcoal fragments testify to widespread fires. The very chemistry of minerals shifted, as acid leached elements from rocks and soils. The earth left behind a detailed archive of its own suffering. The cumulative effect on biodiversity was staggering. Forest ecosystems, once stable and diverse, collapsed into patchworks of survivors and empty wastelands. Plant species disappeared, leaving behind gaps in the food chain. Herbivores that depended on those plants declined, and carnivores depending on herbivores faltered in turn. It was a domino effect, but with no reset button. Insects, often the quiet backbone of ecosystems, suffered catastrophic losses. Some groups never recovered, their lineages erased from the tree of life. The once bustling symphony of chirps, buzzes, and wingbeats grew silent. As acid rain and toxic gases spread, the planet itself seemed to stagger under the weight of chemical assault. Land turned barren, forests burned, rivers soured, and the air became a hazard. The acceleration of catastrophe left no safe haven, no refuge untouched. The earth had become a hostile host, driving out its guests with poison and fire. And yet, as bleak as this stage was, it was not the end. The acceleration was merely another act in the great tragedy, one that pushed ecosystems closer to collapse. But the final unraveling still lay ahead. For now, the focus remains on the land, on the skies, on the corrosive rains and burning forests. The seas had already begun their betrayal, but the land too was now in flames, its air unbreathable, its soils eroded, its forests erased. The acceleration of toxic gases and acid rain was the point at which the Earth's systems stopped wobbling and began to crash. No longer subtle, no longer gradual, the catastrophe grew teeth and claws. Breathing became dangerous. Drinking became corrosive. Growing became impossible. And Earth, if it had whispered before, now seemed to shout, "My air is poison. My rain is acid. My forests burn. Can you survive this?" For most species, the answer was no. On land, the story of the late Permian catastrophe unfolded, with the grim certainty of a tightening vise. If the oceans were being poisoned in silence, the continents were being baked alive in plain view. The land, once diverse and bustling with reptiles, insects, forests, and swamps, began to crack, scorch and unravel under heat that seemed unending. Earth's thermostat had been nudged upward, and the supercontinent of Pangaea became a furnace, its deserts sprawling, its forests igniting, its wetlands evaporating into dust. It was the age of terrestrial collapse, where heat and thirst ruled as merciless kings. The first sign was temperature. As greenhouse gases thickened the sky and volcanic heat radiated into the atmosphere, the average global temperature climbed and climbed again until it reached levels hostile to most forms of life. Estimates suggest spikes of 10 to 15 degrees Celsius above previous norms, enough to turn temperate zones into savannas and savannas into deserts. To imagine this, picture a planet where what was once mild spring became scorching summer, where shade offered little relief, and where nightfall no longer brought coolness. The soil itself baked, cracking in patterns like shattered pottery. Animals crossing the plains left tracks not in mud but in brittle, broken earth. With rising temperatures came drought. Rainfall patterns faltered. Monsoons that once drenched the land with seasonal abundance shifted or vanished. Rivers ran shallow. Streams dried into trickles, and trickles into nothing. Wetlands, those lush refuges of amphibians and plants, shrank into barren depressions. Swamps, which had stood for millions of years as the green lungs of Pangaea, collapsed into cracked basins, their peat dried, their waters gone. Amphibians, creatures tied so tightly to moist environments, faced a gauntlet they could not cross. Eggs desiccated before they could hatch. Adults withered in the heat, their skins unable to retain enough moisture to survive. The croaks and splashes of swamp life faded into silence. Deserts spread across the supercontinent like an invading army. Pangaea, already vast, had long harboured arid interiors, places so far from the sea that rainfall rarely reached them. Now those arid zones expanded, pushing outward, swallowing forests and grasslands, replacing diversity with monotony. The desert was merciless. Where once there had been varied ecosystems filled with shrubs, trees, and small rivers, now there was sand, dust, and heat. Dunes piled upon dunes, winds howled across barren flats, and the horizon shimmered with mirages. Life in these regions, unless supremely adapted, vanished. Forests became tinderboxes. With water scarce and temperatures high, plant tissues dried and weakened. The smallest spark lightning from a storm, friction from falling branches, volcanic ejecta, could set entire forests ablaze, and once ignited they burned fiercely. Trees that had endured storms and seasons for centuries went up in roaring infernos. Canopies collapsed into flame, undergrowth crackled, and thick smoke rolled across the skies. Fires leapt from tree to tree, valley to valley, consuming vast swaths of land. For creatures within, there was little hope. Insects perished in clouds, their fragile wings curling in heat. Reptiles fled, but many were overtaken by flames or suffocated by smoke. Forest fires did not just kill, they erased ecosystems, leaving behind ash, soot, and charred stumps where lush greenery had once thrived. The land itself seemed to rebel. Drought cracked the ground, fires scorched it black, and winds carried away what little topsoil remained. Fertile regions turned barren. Without roots to anchor it, soil blew freely, filling the air with dust. Red and yellow sediment swept across valleys, settling in layers that would harden into stone. Millions of years later, geological evidence of deserts, swallowing continents. The cycle fed itself. Less vegetation meant less moisture retained, which meant less rainfall, which meant more drought. It was a cascade of desiccation, an unrelenting march toward dryness. For animals on land, survival became a grim gamble. Reptiles, the rising stars of the Permian, faced unprecedented challenges. Their scaly skin gave them some protection against water loss, but even they reached their limits. Shade grew scarce as forests disappeared. Prey dwindled as herbivores starved. Herds that once roamed green landscapes found themselves wandering empty expanses in search of food and water, their numbers shrinking with every failed journey. Carnivores that once thrived on plentiful prey found themselves weakened, hunting ghosts across barren plains. Insects, those small architects of ecosystems, also faltered. Heat stressed their fragile metabolisms, drought robbed them of water. Forest fires erased their habitats. Pollinators lost flowers, detritivores lost leaf litter, and predators lost prey. Their disappearance compounded the crisis, as plants struggled without pollination and decomposers vanished from soils. Even the buzz of insect wings, one of the most ancient and persistent sounds of terrestrial life, dimmed into eerie quiet. Swamps and peatlands, which had been ecological anchors, became scenes of desolation. Once these wetlands had stored vast amounts of carbon, building thick layers of peat that fueled the atmosphere with oxygen. But under relentless heat and evaporation, these wetlands' dry cracks spread across their surfaces. Fires consumed the dried peat, releasing yet more carbon into the atmosphere, amplifying the warming. Amphibians perished, plants failed, and the very landscapes that had once been cradles of life became barren scars. The air grew oppressive. Without forests, without wetlands, without the cycling of water through ecosystems, humidity plummeted. Winds scoured the land. Dust storms became common, carrying grit that stung eyes and clogged nostrils. To breathe was to inhale dryness, heat, and ash. Reptiles sought shelter underground, digging burrows into cooler soil, but many did not emerge again. The surface had become uninhabitable for all but the hardiest survivors. There is, strange as it sounds, a grim humour in imagining this landscape. Earth had turned its continents into something like a cosmic oven, set on broil, with deserts as baking sheets, forests as charcoal, and swamps as evaporating pans. Life, caught in this planetary kitchen, was cooked slowly, relentlessly. One can almost hear Earth muttering, "Too hot. Well, I did warn you to hydrate." Geology preserves these tragedies in silent testimony. Ancient sediments show signs of desertification, vast dune fields, frozen in time, layers of ash and soot buried in stone. Fossilized soils reveal chemical leaching, stripped of nutrients by acid rains and fire. Charcoal fragments whisper of forests that burned. Pollen records collapse, showing abrupt losses in plant diversity. Tree rings vanish altogether in some cases, as forests fail to grow. The rocks tell a story of a land gripped by heat and drought, stripped bare of its abundance. For species that had thrived on land, this was extinction by suffocation and starvation, not in the literal sense of air or food vanishing instantly, but in the drawn-out torment of ecosystems failing. Herbivores faced dwindling plants. Carnivores faced dwindling herbivores. Scavengers faced empty carcasses. Amphibians faced desiccated swamps. Insects faced burned forests. Every niche was undermined, every strategy exhausted. The land offered no refuge, only hardship. Forests once stood as strongholds of resilience. Now they stood as blackened ruins. Swamps once croaked with life. Now they lay cracked and silent. Deserts once confined to interiors now sprawled outward like conquerors. The land in its extremity became alien to its own inhabitants. The tragedy of the continents in the Permian extinction lies not just in the death it caused, but in the transformation of landscapes. It was not a single disaster, but a reshaping, a reforging of Earth's face under heat and drought. Places that had been green became gold and red. Ecosystems that had thrived for millions of years were replaced by barren silence. The land, like an old friend, turned unrecognizable, offered no comfort. And yet, even here, amid the infernos and droughts, some creatures endured. Burrowers that could escape heat underground, hardy plants with seeds tough enough to resist dryness, small reptiles adapted to scarcity. These survivors were not the triumphant rulers of the age, but the quiet opportunists, the stubborn holdouts, clinging to whatever scraps remained. Their survival would shape the world to come, but in the moment, their endurance was a whisper against the roar of collapse. The continents of the late Permian were thus transformed into a stage of suffering. Heat pressed down like a relentless hand, drought cracked the land. Forest burned, swamps dried, animals staggered, insects vanished, dust storms swept across horizons. It was a world of desolation, where survival itself became improbable. The oceans had long been the Earth's great refuge, the cradles of life from which all things had once emerged. Through storms and shifting climates, through the rise and fall of continents, the seas had endured as sanctuaries. But in the late Permian, this sanctuary betrayed its inhabitants. What had once been vast blue kingdoms of abundance, transformed into suffocating, corrosive deserts beneath the waves. The slow poisoning that began earlier reached its climax here, and the oceans, which had nursed life for billions of years, became the graveyards of nearly everything within them. The chemistry of the sea turned against its children. Carbon dioxide in staggering amounts dissolved into the waters, lowering pH until the oceans themselves grew sour. Acidification advanced relentlessly. For organisms that relied on calcium carbonate to build shells and skeletons, this was a death sentence. Their protective armor dissolved grain by grain, leaving bodies exposed. Ammonites, once coiled masters of the open waters, found their elegant spirals thinning and pitting. Brachiopods, clams, and corals all crumbled as their very building blocks vanished. Imagine a city where the bricks themselves begin to melt. No wall could hold, no structure could endure. That was the fate of reef systems and shell builders, dissolution from the inside out. But acidification was only the first blow. As the greenhouse effect warmed the planet, ocean circulation slowed, and with it the delivery of oxygen to the depths. Waters that had once been rich and life-sustaining became stagnant, suffocating. The spread of anoxia, oxygen loss, crept outward like a black tide. Deep zones were the first to die, but soon the mid-depths followed, and eventually even the shallows could not be trusted. Entire regions became dead zones where no fish could swim, no invertebrate could crawl, no plankton could thrive. These were not small patches but vast expanses, stretching across continental shelves and open seas alike. For fish, the catastrophe was absolute. Schools that had once shimmered like clouds of silver found themselves gasping in waters that no longer fed their gills. Mass die-offs left carcasses drifting in the currents, piling on seafloors where decomposition faltered for lack of oxygen. The ocean became littered with the bodies of its own children, unrotted and preserved in black, suffocating muds. The fossil record today tells this grim story: layers of organic-rich shale, dark with the unconsumed remains of creatures that perished en masse. The collapse of oxygen and the corrosion of shells cascaded through food webs like falling dominoes. Zooplankton that grazed on phytoplankton weakened. Shell builders vanished. Fish that depended on both suffocate. Larger predators, from swift swimmers to lurking hunters, found their prey disappearing before their eyes. Entire trophic levels collapsed, not one by one, but all at once. It was as though the orchestra of the oceans lost every section simultaneously. The strings dissolved, the horns silenced, the percussion muted, leaving only an empty stage. Even microbes played their part in this tragedy. In oxygen-starved waters, certain bacteria flourished, shifting their metabolism to sulfur. These microbes belched hydrogen sulfide, a gas toxic to most higher organisms. Hydrogen sulfide spread through stagnant waters, poisoning anything still clinging to survival. Where oxygen had once sustained, poison now reigned. If the seas had been difficult before, they were now outright hostile. It was not simply that creatures starved or suffocated, they were poisoned, dissolved, and erased. The reefs, those underwater metropolises, suffered most dramatically. Built painstakingly by generations of small architects, reefs provided shelter and food for countless species, but acid waters stripped their stones, and anoxic conditions choked their inhabitants. The bustling neighborhoods became empty ruins. No corals, no fish weaving between crevices, no crustaceans scuttling in shadow. Only silence, a silence so profound it echoed across evolutionary time. It would take tens of millions of years before reefs returned, re-established by entirely new groups of organisms. The reefs of the Permian were gone forever. The ammonites, those spiral-shelled icons, symbolized the ocean's fall perhaps more than any other group. For hundreds of millions of years they had survived upheavals, thriving as adaptable predators and prey. But in the late Permian, their shells thinned in acid seas, their oxygen needs unmet, their young starved of plankton. Entire lineages disappeared. A few would limp into the Triassic, but most vanished. Their intricate shells frozen forever in stone, monuments to resilience finally broken. Fish, too, declined catastrophically. Some species managed to persist in shallow refuges where oxygen lingered, but even there, the chemical balance was precarious. Many more succumbed, leaving the oceans eerily empty. To imagine a Permian Sea at the height of its crisis is to imagine swimming through water that feels heavy, stale, and toxic, with few shadows darting around, few flashes of scale or shell. The seas were no longer crowded, they were hollow, and in this hollowness lay the full scope of the extinction. The oceans had always been the backbone of Earth's biosphere. They generated oxygen, cycled carbon, and fed ecosystems on land as well as sea. When they faltered, the whole planet faltered. The loss of marine productivity echoed into every corner of the Earth system, starving food chains and altering climates further. But in the moment, the experience was intimate and immediate. A fish gasping, a mollusk dissolving, a reef collapsing, death at every level, everywhere, all at once. One might be tempted to imagine this collapse as a sudden apocalypse, but it was not a single day of doom. It was a process, years and decades of relentless attrition, until at last the cumulative weight of acid and suffocation brought systems down entirely. Life did not vanish in a flash of catastrophe. It dwindled, gasped, withered, and finally yielded. That is perhaps what makes this extinction so tragic. It was not only destruction, but also despair, stretched over time, a slow erasure that offered no reprieve. And yet even here, humor peeks through in the darkest shades. One could call it a cosmic prank of chemistry. Let's see. The Earth might have mused, what happens if I add more acid, turn down the oxygen, and let the microbes belch poison? The answer, of course, was a biological collapse, so profound it left the planet nearly empty. But in this grim experiment, the recipe was clear: no shells, no breath, no survival. A cocktail of doom mixed perfectly. The geological record preserves this disaster in haunting clarity. Black shales tell of oxygen-starved waters. Isotopic signatures reveal carbon cycles thrown into chaos. Fossil layers show abrupt disappearances. Brachiopods vanishing, ammonites dwindling, corals erased. It is not merely absence, but suddenness that shocks. Whole groups once dominant, gone. The rocks whisper of an ocean that betrayed its children, a sea that became unlivable. For the survivors, endurance meant adaptation to extremes. A handful of hardy species, tolerant of low oxygen or resistant to acidification, managed to scrape through. They were not the giants or the elegant forms, but the opportunists, the hidden, the overlooked. Their resilience would seed the future oceans of the Triassic. But in the moment, their persistence was barely a flicker in the overwhelming darkness of loss. The collapse of the marine ecosystems of the late Permian was the most complete unraveling the planet has ever seen. It was not just the extinction of species, but the dismantling of entire ecological architectures. Food webs, biogeochemical cycles, habitats all collapsed in synchrony. The seas had turned against life, and life had no answer. By the end, the oceans, once vibrant, were quiet. No reefs, no ammonite swarms, no teeming shoals of fish. Only scattered survivors drifting in poisoned, sour waters. The cradle of life had become its coffin. If Earth could have spoken, perhaps it would have sighed, "My seas are empty now," but no voice was needed. The silence beneath the waves said it all. If the Permian extinction were a film, it would not be a brief thriller with one climactic explosion. It would be an epic, drawn-out tragedy that began in slow motion, gathered speed in violent bursts, and refused to end even after the worst seemed to have passed. It was not a single event, but a sequence of stages, a build-up, a break and a prolonged aftershock that stretched over tens of thousands of years. This layered pattern is what made the Great Dying so uniquely devastating. Life had endured crises before, but rarely one that came like a creeping shadow, turned into a sudden storm, and lingered like an unshakable curse. The opening act was slow, measured not in days or even centuries, but in millennia. Gases seeped from the vast volcanic eruptions of Siberia, spreading sulfur dioxide, carbon dioxide, and halogens into the air in quantities immense, yet incremental. For the creatures living at the time, these changes were nearly invisible across a single lifetime. A reptile wandering through the forests of Pangaea might not have noticed that the air was fractionally different, or that the rains tasted faintly harsher, or that summers seemed ever so slightly hotter. The shifts were glacial by human standards, but relentless over deep time. Acid rains fell in drizzle after drizzle. Soils thinned imperceptibly. Skies grew incrementally more hostile. For thousands of years, the planet simmered under this chemical and thermal stress, a pot heating 1 degree at a time. But then came the turning point, the sudden break when the pot boiled over. Geological evidence suggests that after thousands of years of build-up, Earth tipped into a cascade of disasters that unfolded with terrifying speed. Oxygen disappeared abruptly from large parts of the atmosphere and environment. Acid rains that had been intermittent now lashed with intensity, stripping away vegetation in waves. Skies darkened with ash, and ecosystems that had been adapting grudgingly to slow stress now collapsed under the weight of sudden shock. Imagine running a marathon for millennia, only to be hit by a landslide in the final mile. Life had been stressed, weakened, and destabilized for so long that when the final push arrived, it was catastrophic. This transition from slow to sudden is part of what made the Permian extinction so thorough. Organisms can adapt to gradual change. Evolution thrives on small shifts, adjusting wings, scales, or behaviors over generations. But evolution cannot prepare for the ground to drop out all at once. And in the late Permian, that is exactly what happened. After thousands of years of poisonous seepage, the atmosphere and environment reached a tipping point where systems cascaded downward. The drop was swift, devastating, and lethal for the vast majority of life. Yet even this sudden phase was not the end. The true cruelty of the Permian extinction lay in its persistence. The collapse did not burn itself out in a decade or even a millennium. It lingered for roughly 60,000 years, delivering wave after wave of devastation. Life tried to recover. Plants sprouted in empty soils. Animals clung to shrinking niches. Survivors attempted to rebuild food webs. But each attempt was struck down by another pulse of volcanic fury, another surge of gases, another shock of acid rain. It was as though Earth kept coughing up disasters in intervals, never allowing ecosystems the time to regain balance. This drawn-out nature gave the extinction its character of despair. In other mass extinctions, there is a sense of singularity, an asteroid strike, a sudden glacial pulse, a sharp blow. But the Permian was different. It was a war of attrition, a siege that wore life down over tens of thousands of years. Imagine living through a storm that never quite ends. The rain weakens, then lashes again. The thunder quiets, then returns louder. Recovery begins, only to be erased. Entire generations of species lived and died in this suspended catastrophe, never knowing a world that was not collapsing around them. Geology bears witness to these stages. In rock records, scientists see signals of gradual buildup, thin layers of volcanic ash, subtle chemical shifts, slow declines in biodiversity. Then come abrupt markers, thick black shales, sudden isotopic spikes, mass die-offs captured in fossil layers, and above them more layers still, further pulses of stress, smaller die-offs, drawn-out periods of emptiness. It is a record of a planet convulsing in phases, as though each breath it took was poisoned, and every attempt to stand was met with another fall. For the creatures that lived through it, the experience must have been bewildering. Imagine being part of a species that endures the early millennia of slow stress, adapting generation by generation. Perhaps you grow smaller, need less food, learn to tolerate harsher rains. Then, in the space of a few centuries, everything collapses. Forests die, food chains collapse, skies darken. If you somehow survive, you emerge into a world barely recognizable. But before you can settle, another wave comes. New eruptions, new poisons, new deaths. Your children's children inherit, not stability, but more calamity. This layering of disaster left scars not only on ecosystems, but on the evolutionary future. The drawn-out nature of the extinction meant that survival was not about weathering a single storm, but enduring a century after century of battering. Species had to be not only resilient but lucky, able to endure repeated setbacks. In some ways, this made the survivors uniquely adapted for the world to come. They were creatures that could endure stress, scarcity, and unpredictability. But in the moment, it must have felt like an endless gauntlet. There is, in this grim sequence, a strange humor of perspective. The Earth, it seems, was not content with a single act of destruction. Instead, it staged a trilogy. Act 1, the slow build-up. Act 2, the sudden collapse. Act 3, the long, drawn-out encore. One could imagine Earth as a dramatic director, muttering, "Too quick? No, no. Let's make it slow, then sudden, then slow again. Keep the audience on the edge of extinction." If this were a cosmic performance, it was overproduced, drawn out, and devastatingly effective. The time scale itself is almost beyond human comprehension. 60,000 years of instability. Entire civilizations could rise and fall dozens of times in such a span. For the organisms of the late Permian, this was not a single event, but an age defined not by abundance or flourishing, but by absence, by the slow emptying of ecosystems. For tens of millennia, life existed not in the promise of tomorrow, but in the shadow of collapse. The legacy of this sequence lies in its thoroughness. By combining slow build-up, sudden shocks, and prolonged aftershocks, the extinction left little room for survival. Ecosystems were destabilized slowly, shattered abruptly, and suppressed continuously. This triple blow explains why the Permian extinction was the most severe in Earth's history. It was not just one kind of disaster, but many, stretched across time, leaving no escape. And yet even here, the story carries a lesson. Catastrophes need not come as sudden strikes from the sky. They can also come as creeping accumulations, small changes piling up until the system tips, followed by long ages of collapse. The Great Dying reminds us that the planet's most devastating tragedies are sometimes not the quickest, but the ones that refuse to end. If Earth could have spoken during this drawn-out calamity, perhaps it would have sighed, "I warned you, I build slowly, I break suddenly, and I linger long," and life, battered and thinned, had no answer but endurance. When detectives piece together a crime, they look for fingerprints, footprints, residues, the silent marks that betray what happened even after the witnesses are gone. Geology plays the same role for deep time. Fossils can tell us who lived and who died, but the rocks themselves preserve the crime scene, layer upon layer, waiting to be read like a file of evidence. And when we turn to the end of the Permian, 25 to 2 million years ago, the rocks give us a dossier of catastrophe, lava flows, frozen in place, isotopic signatures twisted out of balance, chemical anomalies that point to fire and poison, and strata that align across continents to show the disaster was not local, but planetary. Earth, it turns out, left us the receipts, and they are damning. One of the most striking pieces of evidence is the Siberian traps, those vast flood bolts sprawled across what is now northern Russia. To walk across them today is to walk across a frozen lava sea, stair steps of basalt rising in terraces that stretch to the horizon. Geologists estimate that up to 4 million cubic kilometers of lava poured out during these eruptions, enough to bury entire countries under kilometers of rock. The sheer scale is almost incomprehensible. Imagine molten rock, not as a local event, but as a continental flood, lasting not days but millennia. These flows are preserved in layer after layer of basalt, stacked like a geological wedding cake, each tier representing another pulse of eruption. They are the crime scene tape of the extinction, tangible, unavoidable, and impossible to explain away. But lava is not the only witness. Within the sediments that flank these basalts, scientists find chemical clues that tell us about the atmosphere and the oceans of the time. Chief among these are carbon isotopes. Normally the ratio between carbon-12 and carbon-13 remains relatively stable in Earth systems. But during the late Permian, this ratio shifted dramatically. Carbon-12 spiked in abundance relative to carbon-13, leaving an isotopic fingerprint etched into rocks worldwide. What does this mean? It means that massive amounts of light carbon, typically locked in volcanic gases or organic material, were suddenly released into the system. The culprit is obvious: the eruptions of the Siberian traps belching carbon dioxide into the sky. The isotopes are the fingerprints of greenhouse gases, stamped into stone. These carbon anomalies were not local. They appear across continents, in marine sediments and terrestrial deposits alike, showing that the crisis was global. In South China, in South Africa, in Greenland, the same isotopic spike is seen. This is not a local cough, but a planetary fever. Rocks from shallow seas record it, as do deep ocean deposits. Even soils show the mark. It is as though Earth itself signed its confession in isotopes. Yes, I flooded the sky with carbon dioxide, and here is the proof. Another chemical clue lurks in the form of iridium. This rare element is usually locked away in the deep earth or delivered by extraterrestrial bodies, like meteorites. At the Permian-Triassic boundary, thin layers enriched in iridium appear in some localities, not everywhere, not as globally uniform as the iridium spike at the end of the Cretaceous, but enough to raise eyebrows. Was there an impact event in addition to the volcanism? Some geologists argue, yes, pointing to shocked quartz grains, minerals deformed under immense pressures found in the same strata. Others remain cautious, noting that volcanic eruptions can also mobilize trace iridium. But whether or not a meteorite joined the disaster, the rocks carry the signature of something extraordinary, something outside the normal geological processes. The stratigraphy of the Permian extinction reads like a global obituary. At the boundary, layers change abruptly. Rich fossil-bearing beds give way to barren sediments. Limestones, full of shells, abruptly transition to dark shales, recording seas that turn stagnant and lifeless. In continental deposits, coal seams vanish, signaling the collapse of forests and wetlands. Ash layers interleave with sediments, evidence of relentless volcanic rain. It is not just one region, it is everywhere. South America, Africa, Europe, Asia, all tell the same story. The boundary is sharp, sudden, and global. No single continent was spared. Beyond chemistry and stratigraphy, there are physical traces of environmental catastrophe. Paleosols, ancient soils preserved in the rock record, show signs of acidification and nutrient leaching. Minerals within them display unusual weathering patterns, etched by acid rain. Stomatal density in fossilized leaves drops, a sign that plants were struggling with rising carbon dioxide levels. These microscopic features are like the small details in a crime scene, the scuff marks on a door, the broken glass in a window. They may seem minor, but together they testify to a world under assault. Coal, that great archive of ancient forests, also tells a tale of absence. Leading into the extinction, coal beds vanish. For millions of years, lush swampy forests deposited organic matter that compressed into coal seams. But at the Permian boundary, this record disappears almost entirely. It is as if the forests themselves had been erased, leaving no trace to be buried and fossilized. This coal gap is a silence in the geological record, as eloquent as any presence. You cannot burn coal if no forests survive to lay it down. The rocks show us this silence clearly. Some of the most haunting evidence comes from black shales deposited in ancient oceans. These organic rich rocks form when oxygen vanishes from the water, allowing dead matter to accumulate without decomposition. At the Permian Triassic boundary, such shales appear across the globe, layered thickly with preserved organic remains. They speak of oceans that became suffocating, stagnant, and lethal. In them, paleontologists find fossils abruptly cut short, ammonites dwindling, brachiopods gone, fish absent. The rocks preserve the absence as much as the presence. They are the chalk outlines of vanished ecosystems. Geochemistry adds more clues still. Sulfur isotopes show disturbances consistent with massive injections of volcanic sulfur dioxide. Mercury anomalies in sediments link directly to volcanic emissions, leaving a trail of toxic fingerprints across time. Even noble gases trapped in minerals tell the same story. Colossal volcanic outgassing on a planetary scale. Each isotope, each anomaly, is another witness pointing toward the same conclusion that the Earth itself erupted into crisis, and the biosphere paid the price. If all this seems overwhelming, it should. The geological evidence is not one clue but a chorus, each line of data harmonizing with the next. Lava flows map the crime scene. Carbon isotopes provide the fingerprints of carbon dioxide. Iridium offers the possibility of an extraterrestrial accomplice. Stratigraphy lays out the timeline, showing sudden global shifts. Fossil gaps mark the losses, coal gaps the silenced forests, shales preserve the suffocated seas. It is an overwhelming case, as airtight as any detective's file. And yet, as grim as this evidence is, there is humor in the way Earth recorded its catastrophe. Lava flows stacked kilometers high, geology's way of screaming, "Look what I did," carbon isotopes swinging wildly, Earth scribbling in its diary, "Oops, too much carbon dioxide," iridium traces like Fetty from a cosmic guest who may or may not have RSVP'd, coal gaps, a silence louder than words, the Earth muttering, "No trees left, sorry." It is as though the planet, unable to testify aloud, left sarcastic notes in the rocks for us to find. Geologists, with their hammers and spectrometers, act as forensic analysts in this cosmic courtroom. They drill cores, split rocks, measure isotopes, and compare sequences across continents, and the verdict is clear: something extraordinary happened at the end of the Permian, something written not in myths but in magma and molecules. The power of this geological evidence is not only that it proves catastrophe happened, but that it shows how global and interconnected the event was. Lava flows in Siberia align with isotopic shifts in China, with coal gaps in Australia, with black shales in Europe. Each continent tells the same story. Each witness points to the same disaster. This was not local misfortune. This was a planetary crime scene, preserved for eternity in stone. The end of the Permian was Earth's greatest extinction, and the rocks are our testimony. They tell us that lava drowned the land, gases filled the air, isotopes marked the atmosphere, and global strata recorded the silence that followed. They tell us that forests failed, seas suffocated, and life nearly ended. They tell us all of this without words because rocks do not lie. If Earth could speak, it might simply say, "The proof is all around you." And indeed it is. The lava fields, the isotopic ratios, the iridium layers, the barren strata, they are the evidence of the world's greatest catastrophe, preserved in stone, waiting for us to listen. When the rocks tell us what happened to the Earth, the fossils inside them tell us who it happened to. They are not just remnants of bone or shell, not just impressions in stone, they are the voices of the dead, whispering the story of the greatest crisis life has ever endured. And at the end of the Permian, those voices tell of silence, of ecosystems emptied, of lineages erased, of diversity reduced until it barely flickered. If geology is the crime scene tape, fossils are the names on the obituary list. The most dramatic evidence lies in the sudden disappearance of entire groups. Trilobites, for example, had been among the most successful creatures in Earth's oceans for nearly 300 million years. They had weathered crises before, adapted to changing seas, and diversified into hundreds of forms. But at the end of the Permian, their long dynasty came to an abrupt end. In the fossil record, their tracks vanish, their shells no longer accumulate. One moment they are present, and in the next layers they are gone, erased as if an entire chapter of evolution had been torn from the book. The trilobites did not dwindle gracefully into obscurity. They fell like an empire crushed overnight. Other groups suffered equally dramatic losses. The great reef-building organisms of the Permian, such as rugose corals and tabulate corals, collapsed completely. Fossil reefs, once bustling with life, suddenly halt at the boundary layer. Above that line, the stone is barren of their intricate architectures. It is like walking through a ruined city, finding the last building and then only rubble. For tens of millions of years afterward, reefs would not recover, leaving a gap in the marine fossil record that speaks of ecological devastation. In terrestrial ecosystems, reptiles that had begun to flourish during the Permian faced catastrophic losses. Fossil sites that once yield a variety of reptilian forms, large herbivores, sharp-toothed predators, armored oddities, suddenly thin out. Diversity drops so sharply that paleontologists call it not just a decline but a crash. Entire families vanish. Some groups manage to cling on in tiny numbers, but the fossil record makes their struggle plain. Far fewer bones, far fewer species, far simpler communities. What was once a web of complexity is reduced to a skeleton of survivors. Amphibians too show this stark decline. Before the crisis, amphibian fossils are abundant in wetland deposits. Skulls, vertebrae, impressions of their squat bodies and sprawling limbs crowd the rocks. But after the boundary, their presence dwindles to almost nothing. The wetlands that had once been their strongholds are empty, their traces gone. The amphibian fossil record whispers a sad sail of eggs that never hatched, skins that withered, species that left no descendants. Even insects, those usually resilient survivors, are struck down. The fossil record of insect diversity contracts sharply. Wing impressions, body outlines, feeding traces on leaves, all become scarce. Entire lineages vanish without farewell. There is something particularly chilling in the silence of insects, for they are usually the background music of ecosystems. In the Permian fossil record, that music falls away. The buzz, the flutter, the whine, all gone. This collapse in diversity is not just about names disappearing from a list. It is about ecosystems themselves being simplified to the point of fragility. Before the extinction, ecosystems were like orchestras. Many players, many instruments, weaving a complex symphony. Afterward, the fossil record shows ensembles stripped to a handful of musicians, playing only the most basic notes. Food webs collapsed, predators without prey, herbivores without plants, decomposers without material to recycle. What remained was not richness but austerity, a biological world on rations. Coal deposits also echo this biological silence. For millions of years, plant fossils accumulated into thick seams, recording forests and swamps in abundance. At the boundary, those seams stop. The fossil record of plants thins, pollen grains become monotonous, leaf impressions shrink in diversity. It is as if the forests themselves have been reduced to a few stubborn species, clinging where they could. Fossil pollen tells the tale most clearly. Where once there was variety, shapes and sizes ranging across the spectrum, afterward there is uniformity, a few hardy types dominating. Diversity collapsed not only in animals but in plants as well. Fossil assemblages show this simplification everywhere. Before the extinction, you can dig into a layer and find a community, a mix of species, big and small, predators and prey, grazers and hunters, plants of every shape, insects of every wing type. After the extinction, you find only a handful of species repeated over and over, the same survivors in different places. It is like going from a bustling city with countless shops and people to a ghost town with only a few stragglers. The fossils make it plain life itself had been stripped to its minimum. The numbers are staggering. Estimates suggest that over 90% of marine species vanished, and around 70% of terrestrial vertebrates. But the fossils make this statistic real. It is not just a number, it is ammonite shells dissolving, trilobite eyes staring blankly from their last stones, reptilian bones cut off mid-lineage, pollen grains shrinking to monotony. Each fossil is a story cut short, a book that ends without conclusion. And yet, even amid this tragedy, one cannot help but sense a wry humour in the fossil record. It is as though Earth was keeping score, saying, "That group, gone. Those reefs, wiped. Trilobites. Time's up." The rocks do not exaggerate. They are mercilessly honest. Fossils show what lived, and by their absence they show what died. One could almost imagine the Earth stamping its extinction paperwork. Trilobites terminated. Corals terminated. Corals terminated. Amphibians reduced. Insects quieted. Bureaucratic, efficient, devastating. What makes the fossil record especially powerful is its global consistency. In China, in South Africa, in Russia, in North America, the same patterns appear. Layers that once teem with life suddenly go quiet. Fossil diversity plummets not just here or there, but everywhere. It is not local bad luck. It is global catastrophe. The rocks whisper in chorus across continents. This happened everywhere, all at once. The simplification of ecosystems is not just seen in who disappeared, but in who remained. Survivors often show up in fossils as abundant, but monotonous. A few species of small burrowing animals, some opportunistic plants, a handful of hardy invertebrates. They dominate the record not because they thrived in richness, but because everything else had vanished. It is like finding a concert hall where all the instruments are gone except a drum and a flute, banging and piping endlessly because no one else is left to play. The fossil record is not silent, but it is sparse. It is the sparse speech of survivors, the echo of a once great chorus, and this echo tells us that ecosystems were reduced to their bare bones. Where once there was complexity, now there was only survival. Where once there was diversity, now there was monotony. If fossils could speak, they might not use words. They would point to their own absences, the gaps where trilobites should be, the reefs that never grew again, the insect wings that no longer beat. They would say, "Look at who is missing. That is our testimony." And that testimony is damning, for it shows not just extinction, but a collapse of life's variety. And perhaps in a lighter mood, the fossils would shrug and mutter, "We did our best, but Earth was playing hardball." Because even in the darkest record, humour helps us endure. The fossils, then, are our witnesses. They tell us that trilobites died, that corals died, that reptiles and amphibians and insects diminished, that plants shrank in variety, that ecosystems collapsed into simplicity. They tell us that the end of the Permian was not just a thinning of numbers, but a silencing of songs. They tell us, without exaggeration, that life itself nearly ended. And as we listen, we hear not just the silence of what was lost, but the faint persistence of what remained. For in the gaps, in the monotony, in the sparse survivors, lies the seed of what would come next. But that is another story. For now, the fossils speak of loss, and we must let their testimony stand. When the storms of fire, acid, and suffocation finally quieted, when the last great pulses of destruction ebbed, the Earth did not return to normal. There was no quick rebound, no sudden flourishing of life, as though the apocalypse had never happened. Instead, the world after the Permian extinction stood in eerie silence. The oceans were barren, the continents cracked and dry, the air heavy with the ghosts of what had been lost. If the Permian was a banquet of life cut short, then the aftermath was the empty hall, the chairs overturned, the food rotting, and the music gone. 96% of species had perished. It is a number almost impossible to comprehend. Imagine every tree, every fish, every bird, every insect in the modern world. Now imagine all but a tiny fraction of them vanished. The survivors would seem not like the lucky guests after a party, but like stragglers wandering through a city emptied by disaster. The fossil record confirms this emptiness. Ecosystems that had been lush, complex, and interconnected were stripped bare. What remained was not diversity but monotony, not richness but poverty. The oceans, once bustling with reefs, fish, and swarming ammonites, were silent. The water itself had turned into a grave, chemically unstable, its ecosystems erased. Whole trophic levels were gone. No corals built structures, no great schools of fish shimmered in the depths. Only a few hardy organisms clung to existence, often in niches too extreme for their former competitors. Bacteria and opportunistic species dominated, their presence less a sign of resilience than a sign of vacancy. The seas had been demoted from kingdoms of life to shallow puddles of survival. On land, the picture was no brighter. Forests, once sprawling across Pangaea, had burned or withered. In their place stood barren expanses, deserts creeping where wetlands had once thrived, dust storms sweeping across cracked ground. The coal gap that followed speaks of this emptiness. For millions of years, no great swamps or forests laid down the thick organic layers that would one day form coal. The land was stripped, not only of animals but of its green mantle. Even the insects that usually thrive in the shadows of collapse struggled. Their populations shrank, their diversity narrowed. The background buzz of terrestrial life dimmed into quiet. Animals that had once dominated, reptiles with sailbacks, amphibians of the swamps, insect swarms, had been nearly obliterated. Only a handful of lineages crawled through the silence. Small burrowing creatures, opportunistic scavengers, tough plants with seeds capable of waiting out harshness. Evolutionary history at this moment looks less like a grand tree and more like a nearly severed stump with a few shoots clinging desperately to its sides. This desolate aftermath did not last a year, or a decade, or even a century. It lasted millions of years. Recovery was slow, achingly slow by geological standards, and glacially slow by evolutionary ones. It took more than 5 million years for life to regain even a fraction of its lost diversity. Entire ecosystems struggled to reform, stumbling like a patient relearning how to walk after catastrophe. The gap between the vibrant Permian and the recovering Triassic is a long desert of life, sparse and subdued. The slowness of recovery was partly due to how complete the collapse had been. With so many species gone, the ecological infrastructure was missing. Predators without prey, plants without pollinators, decomposers without forest to feed on. It was as though the machinery of life had been dismantled, and Earth was left with scattered parts. Reassembling such a machine takes time, and for millions of years the gears clanked without rhythm, the engines sputtered, and the system refused to run smoothly. There is also the cruelty of timing. Even after the peak of destruction, environmental conditions remained harsh. Temperatures stayed high, oceans remained unstable, and ecosystems could not find equilibrium. The world had been destabilized, and stability does not return easily. Every attempt at recovery faced setbacks, each fragile gain threatened by lingering stresses. Life was not rebuilding on fertile ground, but on scorched earth. Still, some survivors managed to find footholds. Small synapsids, distant relatives of mammals, persisted in the gaps, eking out survival in burrows or shaded refuges. Certain hardy plants spread where others had failed, covering parts of the barren land with green once again. Opportunistic invertebrates carved out niches in the seas, though far fewer than before. These were not triumphant returns, but quiet footholds, the biological equivalent of weeds pushing through cracks in the pavement. Yet in their persistence lay the seeds of eventual recovery. The contrast between before and after could not have been sharper. Before, a world of complexity, trilobites swarming, reefs bustling, forests thriving, reptiles roaring. After, a stripped world, silence in the seas, dust on the continents, survivors scattered and few. The great dying did not just kill, it simplified. It reduced Earth's symphony to a lonely drumbeat, repeating itself without harmony, without chorus. And yet, there is a grim humor in this aftermath. If one were to imagine Earth as a host of a cosmic party, the Permian was the grand feast. Music, dancing, food in abundance. The extinction was the fire alarm that cleared the hall, and the aftermath, that was the janitor, arriving to find the tables overturned, crumbs on the floor, and a single drunk straggler muttering in the corner. Life had not ended, but it was a sad after-party. Is this all that's left? One could imagine the janitor, Earth itself, asking. The answer, whispered by the fossils, was yes, for now. In scientific terms, the aftermath is captured in the fossil record as a lag in diversity. Paleontologists count species in strata above the boundary and find only a fraction compared to before. Food webs, reconstructed from fossils, are simplified, lacking the richness of interconnections. Diversity did not bounce back quickly because the networks that sustain ecosystems had been dismantled. It is like trying to rebuild a library after losing not just the books, but the shelves, the catalogues, and the readers. The shelves of life stood empty for a long, long time. The scale of this devastation reshaped the evolutionary future. By clearing the stage so thoroughly, the extinction gave space for new actors. The Triassic would eventually see the rise of new groups, some of which would dominate for millions of years. Dinosaurs, for instance, and the ancestors of mammals. But in the immediate aftermath, this was not visible. What was visible was emptiness, poverty, a world stripped to its bones. And for millions of years, the Earth wore this emptiness like a shroud. No great reefs, no thick forests, no buzzing clouds of insects. Only survivors, scattered and subdued, rebuilding slowly in the shadow of what had been lost. The aftermath of the Permian extinction was thus not a sudden dawn, but a long twilight, a twilight where the sun seemed reluctant to rise again, where ecosystems stumbled and staggered, where life itself seemed unsure of its future. The silence was profound, the absence overwhelming, the recovery glacial. But in that silence, the first faint whispers of resilience stirred. And from those whispers, given time, a new world would grow. If Earth could have spoken in that desolate aftermath, it might have sighed, "From ashes I will rise again," but not quickly. After the silence, there was movement. After the long twilight of emptiness, small signs of resilience began to emerge. The end Permian extinction had stripped the Earth to its core, but extinction, cruel though it is, has never been the end of the story. Life is stubborn. It creeps back through cracks in stone. It finds refuge in burrows. It hides in spores and seeds. And when the storm has passed, it begins again. So it was after the great dying. A world devastated, yes, but not abandoned. From the fragments of survival, a new chapter began. The earliest ecosystems of the Triassic looked nothing like the lush worlds of the Permian. They were stripped down, simplified, austere. Where once there had been vast forests and intricate reefs, there were now plains of hardy plants and shallow waters sparsely populated. Food webs, once symphonies of complexity, were reduced to skeletal frameworks. But these frameworks were enough. Think of it like a computer rebooting after a crash. The system starts in safe mode, running only the essential programs. The Earth did the same. The ecosystems were minimal, but they functioned. Into this emptiness stepped unlikely heroes. Chief among them was Lystrosaurus, a squat, tusked synapsid with a beak-like mouth and a body built like a barrel on short legs. Hardly glamorous, not particularly fearsome, but immensely resilient. Fossil records tell us that Lystrosaurus spread across nearly every continent in the early Triassic, dominating ecosystems with astonishing success. In some deposits, Up to 90% of vertebrate fossils belong to this single genus. For a time, the world truly belonged to Lystrosaurus. It grazed on tough plants, burrowed into the soil for refuge, and shrugged off the hardships that had undone so many others. If evolution were a talent show, Lystrosaurus would not have won for beauty or charisma, but for endurance and practicality. Other survivors shared the stage, though in smaller numbers. A few amphibians clung to life in remnant wetlands. Small reptiles skittered across the barren landscapes. Insects began to reappear. Tentative wing beats in a world that had gone quiet. Plants, too, pushed back against the void. Ferns, conifers, and seed-bearing pioneers reclaimed the soils, slowly greening the continents once more. These were not grand forests yet, but they were green footholds, patches of photosynthesis spreading like paint across a blank canvas. The oceans also began to stir. Opportunistic species, bivalves, gastropods, and certain hardy fish took advantage of the vacant niches. With the old reefs gone, new kinds of reef building would eventually emerge, though it would take millions of years before corals returned to dominance. For now, the seas were modest, their communities sparse but functional, enough to start the slow work of recycling nutrients, enough to begin laying the groundwork for recovery. Evolution, though slow, is relentless. Once niches are emptied, survivors adapt to fill them. Over time, the bare-bones ecosystems of the early Triassic began to diversify. The world remained precarious for millions of years, with setbacks and secondary crises, but the overall trend was upward. Species counts rose, food webs grew more intricate, plants spread wider, insects multiplied, predators sharpened their tools. The Earth, patient as always, was rebuilding. And from this rebuilding would come innovation. The Triassic, the age that followed the Great Dying, became a crucible of experimentation. Out of the wreckage arose new lineages that would define the next 150 million years. Among them were the archosaurs, a group that included crocodiles, pterosaurs, and most famously dinosaurs. At first they were modest players, small creatures scurrying in ecosystems still dominated by Lystrosaurus and other holdovers. But in time they would rise to dominance, striding across continents, soaring into skies, reshaping ecosystems into forms utterly unlike the Permian past. The ancestors of mammals, too, began their long journey in these recovering landscapes. Synapsids had been battered, but not broken. Some lineages evolved into smaller, more adaptable forms, laying the foundation for eventual mammalian success. In the early Triassic, these proto-mammals were still humble, rat-sized, shrew-like, but their persistence in the shadows would one day yield fur, milk, and the warm-blooded resilience that defines mammals today. What makes this recovery so remarkable is not its speed, because it was glacially slow, but its inevitability. Once life has a foothold, it tends to spread. A plant seed in barren soil can lead to a grove, which supports insects, which feed reptiles, which attract predators. The cycle builds, piece by piece. Fossil records from the Triassic show this gradual increase, species counts rising, ecosystems layering, complexity re-emerging. It is like watching a symphony orchestra slowly return, one instrument at a time. The strings first, then the woodwinds, then the percussion, until at last the music swells again. The dominance of Lystrosaurus in this period offers a lesson in evolutionary pragmatism. It was not the flashiest, nor the most specialized, but it was versatile, robust, and adaptable. When the world was harsh, those traits mattered more than grandeur. For millions of years, this humble creature walked the earth in staggering numbers, a reminder that survival often belongs to the unassuming. Paleontologists joke that if you visited the early Triassic, you'd be tripping over Lystrosaurus everywhere you went, like a world overrun with barrel-bodied lawnmowers, not glamorous but effective. As ecosystems stabilized, diversity slowly expanded beyond these initial monopolies. Other synapsids rose and fell, amphibians regained footholds, insects diversified again, and reptiles evolved into new and strange forms. The Triassic became a laboratory of life, full of experiments. Some lineages would succeed spectacularly, like the dinosaurs. Others would vanish quietly, their fossils the only testimony to their brief moment in the sun. But all of them were part of the same story, life recovering, innovating, and pressing forward after nearly being erased. The contrast between the bleak aftermath and the eventual rise of new diversity is stark. In the worst of the extinction, ecosystems were stripped to almost nothing. In the recovery, ecosystems became sites of rebirth. Each fossil layer from the Triassic tells of incremental gains. A new plant type here, a new predator there, a community expanding in complexity. It was not a sudden renaissance, but a steady climb. And by the time the Triassic matured, the Earth was once again teeming, not with the same species, not with the same patterns, but with life nonetheless. This resilience carries with it a certain humor too. One can imagine the Earth, after nearly wiping the slate clean, muttering to itself, "All right, let's try that again. This time with dinosaurs." It is as though the planet, having run one experiment into the ground, decided to reboot with a new cast. And what a cast it would be! From tiny scurrying proto-mammals to towering sauropods, from crocodile-like archosaurs to winged pterosaurs. The Triassic was the pilot episode for the Age of Dinosaurs, and the script was written in the ashes of the Permian. The slow recovery also highlights the patience of evolution. Unlike a human rebuilding project, there were no shortcuts, no quick fixes, no instant returns. Each lineage had to adapt. Each ecosystem had to stabilize. Each interaction had to be rebuilt. It was painstaking, methodical, and relentless. And in that relentlessness lay the triumph. Because by the Middle Triassic, life had not only recovered, but reinvented itself, ready for a new era of dominance and diversity. From a scientific perspective, the recovery is visible in increasing fossil diversity, in the reappearance of complex food webs, in the return of forests and reefs. From a more poetic perspective, it is visible in the sheer persistence of life. The fact that, after losing nearly everything, Earth still found ways to be green, to be filled with motion, to be alive. And if we allow ourselves a touch of humor, it is almost as if the Earth, exhausted from catastrophe, finally stretched, yawned, and said, "Well, that was dramatic. Now where were we? Ah yes, life." The recovery after the Permian extinction was not quick, not easy, not glamorous, but it was real. From the stubbornness of Lystrosaurus to the rise of dinosaurs, from the sparse beginnings of the early Triassic to the flourishing ecosystems that followed, it was the story of life refusing to give up. The banquet had ended, the hall had been emptied, but the music began again, softly at first, then louder, until a new symphony filled the world. If Earth could have spoken then, perhaps it would have whispered, "Hold on, we are starting over." Slowly but surely. When we look back at the Permian extinction, it is tempting to treat it as ancient tragedy, an event so distant in time that it seems more myth than memory. 252 million years is beyond comprehension, longer than any lineage of humans, longer even than the reign of the dinosaurs. But the rocks tell us it was real, the fossils tell us it was devastating, and the chemistry tells us it was driven in large part by the same forces we tinker with today: the warming of the planet, the flooding of the atmosphere with carbon dioxide, the destabilization of climate and ecosystems. The Permian is not only a chapter in natural history, it is a mirror held up to our present. The first lesson is written in carbon. During the Great Dying, volcanic eruptions in Siberia poured billions of tons of carbon dioxide into the atmosphere. That gas trapped heat, raising global temperatures by double digits, melting stability into chaos. Oxygen vanished from seas, acid rain scarred the land, and ecosystems unraveled. Fast forward to today, we are adding carbon dioxide not with volcanoes but with smokestacks, tailpipes, and burning forests. The source is different, but the mechanism is the same. The Earth does not care whether the gas comes from magma or machines. The chemistry is identical. Too much carbon dioxide, and the climate tilts. The numbers are sobering. During the Permian, carbon dioxide levels rose dramatically over tens of thousands of years, overwhelming natural systems. Today, we are raising levels at a rate hundreds of times faster. What took millennia in the Permian, we are achieving in centuries. If the Earth were a chemistry teacher, it might raise an eyebrow at us and say, "Really? You saw what happened last time and you're speeding it up?" The second lesson is the fragility of oxygen. During the Great Dying, oxygen vanished from vast stretches of the oceans, and even faltered in the atmosphere. Life suffocated not just in one place, but everywhere. We often take oxygen for granted, assuming the air will always be breathable, the seas always livable, but the Permian shows us that when climate shifts far enough, oxygen is not guaranteed. The balance is delicate, and once disturbed, recovery is slow. The third lesson is about interconnectedness. In the Permian, extinction did not strike species at random. It struck ecosystems as systems. When plants faltered, herbivores starved. When herbivores starved, predators collapsed. When reefs dissolved, fish lost habitat, and food webs crumbled. The Great Dying was not the fall of isolated dominoes, but the collapse of the whole board. Today, our world is similarly interconnected. When pollinators decline, crops suffer. When coral reefs bleach, fisheries falter. When forests burn, carbon surges and climates shift further. We are not isolated from these processes. We are woven into them. The Permian reminds us that when the web frays, it can unravel entirely. The fourth lesson is about time. The Permian extinction was not only devastating but prolonged. It lasted tens of thousands of years, and recovery stretched into millions. Once ecosystems collapse, they do not spring back like rubber bands. They stumble, they crawl, they reinvent themselves slowly. For humanity, that means prevention matters. If we push systems to collapse, we cannot expect a quick fix. We cannot assume technology will conjure instant replacements for rainforests, reefs, or pollinators. Once gone, complexity takes ages to rebuild. If Earth could speak, it might quip. Extinction is quick. Recovery takes longer than your species has existed. And then there is the humbling lesson of scale. The Permian extinction eliminated 96% of species. It was the closest life has ever come to total erasure. And yet, life itself persisted. Not the mighty, not the specialized, but the hardy, the adaptable, the unassuming. Evolution favors resilience, not grandeur. Humanity, for all our intelligence and technology, is not exempt. We are one species among millions, bound by the same physics and chemistry as trilobites and ammonites once were. We cannot stand apart from the Earth's systems. We stand within them. There is humor to be found, even in these grim parallels. One could imagine Earth holding up a sign reading Permian extinction caused by carbon. Do not repeat. And here we are, scribbling over it with our own emissions, saying, but what if we try it faster? If history is a teacher, then we are the students who ignore the warning on the blackboard, only to trip over the same lesson again. Yet the purpose of looking back is not despair, but clarity. The Permian shows us what can happen when the climate is destabilized beyond a tipping point. It shows us how quickly abundance can vanish, how thoroughly ecosystems can be stripped. But it also shows us that choices matter. Life did not end. It staggered, it shrank, it suffered, but it endured. We, with foresight and knowledge the trilobites never had, can choose not to trigger such devastation. Protecting the environment is not a luxury or an afterthought. It is survival. To keep carbon dioxide in check, to preserve forests, to guard reefs, to respect the balance of oxygen and carbon, is to avoid reenacting the worst chapter in Earth's history. The lesson of the Permian is not that catastrophe is inevitable, but that catastrophe follows from imbalance left unchecked. And we should remember that resilience is not guaranteed to the same degree for all. The survivors of the Great Dying were not the dominant, not the beautiful, not the complex. They were the humble. If we drive ourselves into collapse, we cannot assume humanity will be among the survivors. Earth will endure, life will endure, but our species may not. The rocks are not sentimental, they do not preserve privilege. The Permian extinction whispers across 22 million years, not in myth but in data. Carbon spikes, oxygen crashes, fossils vanish. It is a whisper we would be wise to hear, for it says, I have done this before, I can do it again. If Earth could leave us one final note from that age, perhaps it would read, learn or repeat. And if we laugh at that note, so be it. But better to laugh and learn than to laugh and fall. We have travelled far together, across hundreds of millions of years, into an age so ancient it seems almost a dream. The Permian extinction, the Great Dying, was not a single moment but a sweeping saga, an unravelling of life on a scale our planet has never seen before or since. It was a story written not in words but in magma, in gas, in fossils and in silence. And now, as we arrive at the end of our journey, it is time to look back, to gather the threads together, and to let the story settle gently in our thought. At its heart, the Great Dying was not caused by one culprit, but by many working together in dreadful harmony. It was the orchestra of catastrophe, volcanism releasing unimaginable quantities of carbon, oceans warming and suffocating, skies darkened with acid and ash, landscapes withering under drought and heat. Some scientists suspect even a cosmic visitor may have joined the chorus, leaving traces of iridium behind. Each factor by itself would have strained the biosphere. Together they were overwhelming. Earth tipped into a spiral it could not escape, and the cost was staggering. 96% of species lost, ecosystems dismantled, the planet silenced. The pace of this catastrophe was as striking as its causes. At first, it was a slow accumulation, gases seeping, temperatures creeping upward, ecosystems wobbling but persisting. Then, suddenly, the tipping point came. Oxygen vanished, acid rained, chains of life snapped in a cascade. But it did not end quickly. The calamity stretched across tens of thousands of years, striking in pulses, refusing to release its grip. For life, this was not a storm to endure, but a new age of hardship. Survival meant not just resisting a single blow, but enduring a relentless siege. The evidence is etched everywhere. Lava flows frozen in time across Siberia, carbon isotopes shifted in sediments worldwide, fossils that vanish from one layer to the next, leaving gaps that speak louder than presence. Coal seams ending abruptly, black shales recording suffocating seas, pollen records reduced to monotony. Together these testimonies form a chorus of stone and bone, whispering the same truth. Something extraordinary happened. Something global, inescapable, transformative. The aftermath was silence. Oceans stilled into barrenness, continents cracked and dry, ecosystems simplified to their barest bones. But in that silence, life did not vanish completely. Survivors, humble and hardy, began the slow work of recovery. Step by step, generation by generation, the earth rebuilt its green and blue mantle. From the ashes of the Permian came the dawn of the Triassic, and in time, the rise of new dominions, the dinosaurs, the first mammals, the forests of a new world. Life proved not only fragile but also resilient, capable of collapse, yet also of rebirth. For us today, this story is not merely ancient history. It is a reminder written in fire and stone. The forces that shaped the Great Dying are not alien to us. Carbon dioxide, warming, oxygen loss, these are processes we know intimately, processes we influence now through our own actions. The Permian tells us what happens when balance tips too far. It warns us that systems we think stable can falter, that abundance can vanish, that recovery once collapse begins is not quick. It tells us too that resilience exists, but resilience is not an excuse to court disaster. And so the Great Dying speaks across time, not with despair, but with wisdom. It tells us that Earth is vast but vulnerable, that life is rich but delicate, that choices matter. It tells us to look at our forests, our oceans, our atmosphere, and to see them not as unshakable backdrops, but as living systems, capable of change, deserving of care. It invites us to humility, to wonder, to responsibility. There is even humor in the telling. One can almost imagine Earth rolling its tectonic eyes and muttering, "I've shown you this lesson once before. Do try not to repeat it." The rocks may not laugh, but perhaps we can, gently at the absurdity of ignoring a warning carved so clearly into the planet itself. And so we close this journey, not with fear but with reflection. The Great Dying was the darkest chapter in life's history, yet it was also a turning point. From devastation came renewal. From silence came new song. That is the rhythm of earth, destruction and creation, loss and renewal, endings and beginnings. As you rest now, let that rhythm soothe you. Imagine the deep time we have walked through, the lava flows and forests, the oceans rising and falling, the fossils whispering their stories. Imagine the fragility of life, but also its resilience. Let it be both a caution and a comfort that we are part of this great story and that the choices we make are chapters still being written. If Earth could speak to you tonight, perhaps it would say, "Sleep, dream, and remember. My history is your lesson, my resilience your inheritance. Learn, cherish, and live with care." So share your thoughts if you wish. Let others know what this story means to you. Press the like button if you found wonder here. Subscribe to continue wandering with me through time and space. And now, close your eyes, let the weight of history rest lightly on your heart, and drift into dreams where Earth is always alive, always changing, always teaching. Good night.